Jai Hind everyone. I am Anupam Kumar Saini, Assistant Professor, IT Department, AKGEC. Today's my topic is Hasse Diagram. This is the topic of Discrete Mathematics that is taught in second year. So, what is Hasse Diagram? Hasse Diagram is a graphical representation of the relation of elements of a partial order set with an implied upward orientation. It means Hasse diagram represent the relation of element that are partial order set. And what is partial order set? A partial order is a binary relation over set P if it is reflexive, antisymmetric and transitive. If a relation fulfills these three conditions, then that relation is known as partial order. Then reflexive relation, if a relation is reflexive, then all the element of AA should be belongs to the set A, then it will be reflexive relation. We can say that if a set have element A, B and C and a relation is given here A comma A, A comma B, B comma B and C comma C. If this is a relation R1, we write it as a R1. Here a relation A belongs to A means A is here, B relation of B and B is given, a relation of C and C means all the elements with the relation itself is given in the relation, then it will be reflexive relation. The second one, antisymmetric. A relation is antisymmetric if a relation have relation of element have A comma B and B comma A, then A should be equal to B. For example, if element 1, 2, 3, a set A have element 1, 2 and 3 and relation R2 is given here 1, 2, 2, 1, 1, 3, here relation A comma B belongs and B comma A belongs, but A is not equal to B. Here A related to B and B related to A, but value of A is 1 and value of B is 2 and A and B are not equal to A and B are not equal. So this is not a antisymmetric, is not a antisymmetric. So R2 is not antisymmetric here. If a relation 1 1 2 2 and 3 3 comma 2 3 are given here. In another example, if you take R3 as a 1 1 2 2 3 3 and 2 3, this is 2 3 is here. So we check that A belongs to B, A comma B related to R, B comma A related to R means this is A, this is B, this is belong to R, and this is B and this is A. We take as a or as a B, both are equal. Then A comma B belongs to R and B comma A belongs to R. A subset of B, B subset of A, then A equal to B. That means A comma B belongs to R, B comma A belongs to R. Then we have to check A equal to B. If A comma B belongs to R, B comma A belongs to R, then we have to check A should equal to B. So here A comma B belongs to R, B comma A belongs to R, and both are equal. In this, A comma B belongs to R, B comma A belongs to R means first we consider A and this one is B. Next we consider it as a B and as a A. So both are equal. Same for 3 and 3. Then the relation should be antisymmetric. For R3 is antisymmetric here because 2 comma 3 belongs to R, 2 comma 3 belongs to R, but 3 comma 2 not belongs to R. So don't need to check A equal to B. If both belongs to R, then we have to check A should be B, then it will be antisymmetric. Here 2 comma 3 belongs to R, but 3 comma 2 is not belongs to R. So the given relation R3 is antisymmetric. Third one is represent the transitivity, means transitive relation. A comma B belongs to R, B comma C belongs to R. Then we have to check A comma C should be belongs to R. We take other relation 1 2 1 1 2 3 3 3 3. Here we check the transitive relation. A comma B belongs to R means A as 1 B 2, then 2 3, B C belongs to R, B C belongs to R. Here A C should be there, means if A is 1, B is 2, B is 2 and C is 3, then there should be 1 and 3. 1 and 3 should be there in relation. Then this relation will be transitive relation. But in this case 1 comma 3 not belongs to R, then this relation is not transitive. If we take 1 comma 2, 1 comma 3, 2 comma 3, 1 comma 1, here we check for R5, it is transitive or not. A B, B C, A C is here. For other relation 1 1 means A B, we take 1 1 as a 1 as a 1 as a B, and B C, then there should be A and C in the relation 1 comma 2, that is also available here 1 comma 2, then this relation will be transitive. So if a relation fulfill these three criteria, then the relation is considered as a partial order relation. The power set of A when the elements are A comma B comma C, then find out the power set of A. So if the element n number of element in a set, then number of element in power set should be to the power n. Here number of element is 3, then to the power 3, that is 8, then number of element in power set should be 8. As we know, phi is a subset of every set. So we take phi first element, then A, B, C are the three elements in a set, then we find the subset of all the elements, A as a subset, B subset, C subset, then combination of A, B, C, A, B here, A, C here, B, C, and complete element A, B, C is here. Then number of elements are 8 in power set. Set here we have to check the power set of A is partial order set or not. Like the previous example, we if it fulfill these three conditions, then it will be power this power set will be the partial order set, reflexive, antisymmetric and transitive. So this is the basics of Hasse diagram. Now we move to our topic, Hasse diagram. First step to draw the Hasse diagram. There is 4 steps to draw to construct Hasse diagram. List the element and their relationship. First we find out the elements which we construct for Hasse diagram. Write down all the elements in the set and figure out how they are related. Less than, greater than, divides, which operation we apply accordingly. Then draw all elements as dot. Connect related dots. Then we have to connect related dots, means draw a line between each dot. Fourth step, remove unnecessary conditions, means if there is a transitive relation, means if there is a relation A comma B there, B comma C there, and A comma C is also present there, then not need to draw A comma C. In fourth step we can say it, remove transitive relation. We take an example, draw a Hasse diagram for D12. Operation apply here, divisible. Then divisors of 12 will be 1, 2, 4, 6, 1, 2, 3, 4, 6 and 12. 1, 2, 3, 4, 6 and 12. These are the divisors of 12. Then we have to construct a Hasse diagram for it. This Hasse diagram follow the approach bottom up approach. We take smallest element 1, then upper element is 2, that is divisible by 1, and 3, that is divisible by 1 but not divisible by 2. So we take it as a parallel. Then next one is 4. 4 is divisible by 1 and divisible by 2, and 1 is 3 is divisible by 3. Next one is 6. 6 is divisible by 2 and 3. And 12 is divisible by 4, 6, 2, 3, 1. this is a structure of D12 means divisor of 12, but it is not a Hasse diagram, as we see that in step 4 we have to remove all transitive relation. Then 1 2 is here, 2 4 is here, then we have to remove 1 4, means 2 is divisible by 1, 4 is divisible by 2 and 4 is divisible by 1. So we have to remove it. As same concept, 4 is divisible by 2, 12 is divisible by 4 and 12 is divisible by 2. Then we have to remove this transitive relation and so on. We have removed all transitive relation. The final Hasse diagram we get here. Next example, consider the poset where p equal to 1, 2, 3, 4, 6, 12. This is the same example in different language. What is maximal element and what is minimal element? Maximal element is an element of poset that is not less than any other element of poset, or we can say that the element that is not related to any other element, means topmost relation should be maximal element. Same, minimal element and element poset that is not greater than any element, means smallest element of Hasse diagram is minimal element. This is the other example. Draw Hasse diagram for 3, 4, 12, 24, 48, 72. Find the maximal, minimal, greatest and least element. Here what will be the maximal element? Maximal element will be, as definition say, no other element should be greater than that. Then maximum element of this Hasse diagram is 72 and 48. 72 and 48 will be maximal element. Minimal element should be 4 and 3 here, because no other element is less than that. So minimal element are 3 and 4, and greatest element does not exist here because greatest element should be unique. Since there is no any one element that succeed all the elements, and least element does not exist here because it should also be unique. So here only maximal element and minimum element we find. If we consider 1 here, then what will be the minimal element? Least element? Least element will be 1 in this case. So this is the Hasse diagram. Okay.